All right, so we're going to continue here. There's a discrepancy between the actual mass and the calculated mass. And so let's go back and do this for one of these. Have the masses here. We know the composition of fluorine-19. Let's go ahead and calculate the mass and then compare it with the actual mass. So fluorine-19 has 9 protons, and so this would be 9 times 1.073 U, which gives us how many? Can somebody calculate this for me? Okay, 9.06588. How many sig figs are we allowed? This is 5. 9 is what? We don't use 1. 9. Can you have a tenth of a proton? Is that physically possible to have a tenth of a proton? 9 is going to be exact, right? And so we'll just consider this 9.06588. So we're going to go out to 5 sig figs and then subscript the insignificant 1. We'll just carry 1 extra in this calculation. Okay, then we have 9 electrons. The 9 electrons are going to be point to the 000, 5, 4, 858 U. Can somebody calculate this?
I got 4.93722 times 10 when I get a third.
Okay, I don't want it in scientific, so I'm going to convert it times 10 to the negative 3, right? And so we'll go 0.00493 722, and then we'll carry 1 extra. So it's 5 sig figs here as well. And then we have 10 neutrons. Did everyone see how I calculated this? I'm assuming this is pretty straightforward. The 10 neutrons is going to be 10 times 1.0087 U. And this should give me 10.087 U. All right, now looking at the decimal places, we're going to do an addition now. And so how many decimal places am I allowed? Well, I have 4 decimal places here. I have 7 here and 3 here. So the smallest number of decimal places is 3. So I'm only allowed 3. It's going to be looking like that. I didn't draw it so neat. Okay, so let's go ahead and add these up. This is going to be 2, 2, 7. And then 8 and 3 is 11. 9 and 9 is 18. Okay, these are insignificant. And then carry the 1 over here. So 5 and 5 is 10. Plus 7 gives me 17. And that's 7, 0, and 8 is 15. It's going to give me 1 and 19. I get 19.157 U, according to my rules of sig figs. Now, are sig figs, is a rule like a law? Is the rule the same thing as a law? Actually, not yes, it's no. Rules are not the same as law. Why? this, everybody has their own particular definition, but this is the definition we're going to use for this class. A rule is not a law because rules have a lot more exceptions, right? Rules have a lot of exceptions. If a law had a lot of exceptions, it wouldn't be a very useful law, that's for sure. If Newton's law had, well, it works except for this, except for that. There could be exceptions, In fact, Newton's law does have an exception, one major one. Newton's law is what we call classical physics, so it only works for big bodies. Small bodies, it doesn't work so well. But the sig fig rules, are there exceptions there? Do they always work? No, they don't. And so tell me, is this a fair, when I calculate this, is this a fair representation of the uncertainty in the combined masses? We followed the sig fig rules correctly, yes, we did. But did it work in this particular case? Did you guys review that homework problem? Sig figs? Yeah, it's very similar to that. Did it work in this case? What's the worst precision that we have in our original data? When I think about the mass here, the mass, remember we were talking about the plus or minus? This mass is plus or minus quadruple 0, 5. This mass is minus 0.00005, right? This mass is plus or minus quadruple 0, 5. This mass is plus or minus triple 0, 5. Is that fair? No. And so here's a case where I probably would have ignored sig fig rules and would have written it like this. Even though we aren't allowed that, it makes more sense because all the original data masses were to that precision, so therefore, this combined should be roughly to that precision. But anyway, we get this mass. It doesn't matter if you do that or not. This is just something. And then I told you there's better ways of handling this later. Or we just carry it down. Okay, so this is the calculated mass. Then we weigh this in a mass spectrometer. Fluorine-19 is easy to weigh because fluorine-19 only has one naturally occurring isotope. All the atoms of fluorine in nature are fluorine-19. That's what it means to have one naturally occurring isotope. There are radioactive isotopes of fluorine, but we aren't going to worry about those because those don't live for very long. But fluorine-19 in nature, and you don't really find any radioactive, these are man-made radioactive isotopes of fluorine. If you shock this in a mass spectrometer, since they all weigh the same, they all hit the detector in the same spot. And then we can weigh it. Well, how the heck do you calibrate one of these things? Do they have an atom stored in a vault somewhere in Washington, D.C., saying that this is how much 1 U weighs exactly? Do you know how much 1 U? Is there something that weighs exactly 1 U? There should be, right? Because there's something that they say weighs exactly 1 kilogram or as close to it as you can get, and that's called the standard kilogram, right? It's locked away because it's valuable. And everybody else uses that to make their own version of we buy it, much cheaper version, right? We couldn't afford the real one, of course. So is there somewhere at the National Bureau of Standards, or whatever they call it now, where they keep a 1U mass so that we can calibrate our mass spectrometer, which reads in U. Well, let me ask you, is there such thing as a 1U mass? First question. Is there such thing as a mass that weighs exactly 1U? Or close to it? Okay. Carbon-12, yes. The hydrogen atom, oddly enough, does not weigh 1U. You would think the hydrogen atom would weigh 1U, but it doesn't. It doesn't weigh 1U. In early, in early atomic theory, some people hypothesized that all atoms were a multiple of hydrogen. And so all the other atoms were just some integer times the hydrogen atom. Unfortunately, it didn't work because they didn't know the nuclei can have different numbers of neutrons, right? But it was close. I mean, they were close. They just didn't know about neutrons. But it is the carbon. But the carbon-12 atom, this is why I asked you about carbon-12. Carbon-12 atom does not weigh 1U. Do you know how much the carbon-12 weighs? The carbon-12 weighs 12U. Right? Carbon-12 weighs 12U. But you need to have this memorized, because the mass of a carbon-12 atom is the definition of the U. The carbon-12 atom is exactly 12U. And so one atom of carbon-12 is defined as 12U. Since you cannot slice a carbon atom into 12 equivalent pieces, there's no such thing as something that weighs exactly 1U. This is important because this is how we're going to calibrate this. Now, if we have some carbon-12 atoms, we vaporize those into the gaseous state, and then where they hit the detector, that's exactly 12U. And then everything else we can measure relative to that. Does that make sense? Carbon-12 is the new standard. You know what the old standard was? The old standard mass for the U was, I think, chlorine. And so, or was it oxygen? Gosh, no, it was oxygen. The old standard mass was an oxygen-16. They used to define the U as being a single atom of oxygen-16 weighs exactly 16U. And so if you go back into the masses, and if you're looking at a book from the 50s, all the masses are different. You look at a periodic table from the 50s or table of isotopes. The table of isotopes gives you all the isotopic masses. All the masses are totally different. The masses are totally different because they used a different calibration standard than we use now. High purity carbon-12 is easy to get and easy to use. And so that's how we can calibrate this. Once we get it calibrated, then we'll shoot in fluorine-19. Fluorine-19 is going to land out here, somewhere out here, and then we can weigh it. The mass of fluorine-19 is given on the periodic table. The average fluorine atom, well, all the atoms are the same, are going to have that mass, 18.998403. And so the actual mass is 18.998403U. Look how precise this mass is. Where do you get that kind of precision? Where you get this kind of precision is by buying a very expensive mass spectrometer. Very expensive, that can just measure these tiny differences in where the detector strike occurs. That's a lot of sig figs, isn't it? And so this is the weighed mass. It's the weighed mass with the definition of the U being based on this, carbon-12. And so which one is fact? Is our calculation fact, or is the experimentally observed mass fact? Which one is fact? One of these is wrong. Fluorine 19, calculated mass is 19.1578. The weighed mass is 18.9984. Which one of these two is wrong?
The 19.
The 19. This is wrong. We can't do this. There's a conflict between the two masses. It can't be both masses. It's one mass. And we know that experimental fact is fact, right? And so whatever theory we have has to agree with fact. Well, the theory is, did we measure these masses wrong? No, these masses are correct. The theory is how they're put together, in the nucleus. That was wrong. Right? And so this is wrong, and it's wrong because of the mass defect. The calculated mass is always going to be greater than the actual mass because some of the mass has to be converted into nuclear binding energy. Okay. And so if we need to know the mass of an atom, of an isotope, we always have to weigh it using a mass spectrometer. We can never calculate it. Although calculating would be a lot easier. All right, but the mass spectrometer gives us additional information. All fluorine in nature consists of a single isotope, fluorine 19. Phosphorus in nature consists of a single isotope, phosphorus 31. There's also phosphorus 32, but that's a man-made one and it doesn't occur naturally. And so all phosphorus atoms in nature weigh, 30.97376 U. All of them do. But hydrogen atoms, are you going to find a hydrogen atom that weighs 1.007 U? No. Because hydrogen atom consists of multiple isotopes. And the masses up there in black are the average of all the isotopes. Right? And so the mass spectrometer gives us additional information. So if we were to shoot mercury atoms in here, how many strikes on the detector would we get? We'd get 1, 2, 3, 4, 5, 6, 7. And so there are 7 different masses that are found in mercury atoms in nature. In other words, there's 7 different isotopes of mercury found. And we could get the masses, even though you look at the mass 204, but you can be very precise here. Like this one's just slightly above 202. And you could get that to like 6, 7, 8 sig figs of precision to get that mass. It's roughly 202, but to 8 sig figs is 202 point something, something, something. Not only can you figure out how many, so we have 7 different isotopes of mercury. One weighs close to 196, one weighs close to 198, close to 199. We can get their masses to a high degree of precision, and we can get something else to a pretty good degree of precision, and that is how many atoms strike. For example, for every one of these, we get 5 of these. And what we call that is a percent natural abundance. And so, depending on how many strikes we get, the most abundant isotope of mercury we can determine easily from the mass spectrum. The mass spectrum tells us the one at about 202 is the most abundant. The least abundant mercury isotope would be the one around 196. And so, since the masses and the mass number are approximately the same, this is mercury 196 is the least abundant, mercury 202 is the most abundant. What's the actual mass? The actual mass we'd read from the mass spectrometer. We normalize all these peaks, we can get what we call the percent natural abundance. So looking at the percent natural abundance here, mercury 202 is 29.8, mercury 196 is 0.146%. The masses, they don't write here, but the masses we'll find in a table. Okay. So how can you weigh single atoms with a mass spectrometer? Do you know you can weigh molecules too, single molecules? How do you think you can weigh a single molecule? What instrument do you think we could use to weigh a single molecule with? A mass spectrometer. And so with mass spectrometer, we just shoot molecules instead of atoms. And we have to be very gentle with molecules because molecules, the bonds can break and they can fragment into lots of different pieces. And so if you're gentle with ionizing them, then you can weigh these individually as a whole, or they break apart into fragments and then you work backwards, put them back together into a single molecule. All right, so now what we're going to do is try a homework problem. I'm going to try homework problem number 80 here. Okay, the two naturally occurring isotopes of chlorine are chlorine-35. Chlorine-35, where does this data come? They give us chlorine-35 weighs 34.9689 U. How did they get that mass? Mass spectrometer. Chlorine-35 consists of 17 protons, 18 neutrons, and 17 electrons. Did they combine the masses? Could you do that? No, you can't combine the masses because of the mass defect. And so they weighed it. They see it's 75.77% abundant. 75.77% abundant, where did they get that from? Versus chlorine-37. Chlorine-37 weighs a little more, 36.9658 U, and it's only 24.23% abundance. There are only two isotopes, so these two percentages add up to 100%. Where did they get the percentages from? How could they figure out, you know, if you have a sample of chlorine, let's say you had 1 billion chlorine atoms, how did they know that 75% of those are chlorine-35 and 25% of those are chlorine-37? How did they determine that? By using a mass spectrometer. And so those two pieces of data can be easily obtained by a mass spectrometer. And so you look at what is the average mass of chlorine? If I look on the periodic table, the average mass of chlorine is 35.453. 35.453. Is there an atom of chlorine in nature that weighs 35.453 U? No. No. No, there's no such thing as an atom that weighs 35.453 U for chlorine. Why? Because this is the average of the two isotopes, right? We have this equation. It's going to be 75.77, a percent is part per 100. And so 75.77 out of 100 of those are going to weigh 34.9689 U. And 24.23 out of 100 will weigh 36.9658. And then that's going to equal the average. This is the average of the two. It's a weighted average, right? Is this familiar? Because I was planning to skip this entirely because this is pretty basic, I think, calculation. Is it? All right. How about fluorine 19? Are there any fluorine 19 atoms in nature that weighs 18.998403 U? Are there any fluorine 19? This is the average, right? And so are there any fluorine 19 atoms in nature that weigh this amount? Yes or no? There are no chlorine atoms that weigh this amount, but are there fluorine atoms that weigh this amount in nature? All of them do, because 100 out of 100 consists of 18.998403 U. Fluorine 19 is 100% natural abundant, so all of them weigh this amount. That's the mass of a fluorine 19 atom. Does that make sense? So how do you know which of those elements on the periodic table consists of multiple isotopes and which of the elements consists of a single isotope? I told you that fluorine is a single isotope, and what else is a single isotope? Natural abundance.
Carbon?
No, carbon is carbon 12 and carbon 13. You can tell, you know, in nature we have carbon 12 and carbon 13. Look at the average. The average is 1201. So which one's more abundant? Carbon 12, it's got to be 99% abundant, right? If you get the 1201. If the average mass was a 12.9, then it would be like 90% abundant for carbon 13. Phosphorus 31. There are others, but those are the two most important ones. We have fluorine 19 and phosphorus 31, plus others. And so here's where having some memorization helps a little bit for certain questions. And so if we look at a chlorine sample in nature, you know, we see two types of atoms: a lighter chlorine atom and a heavier chlorine atom. And any chlorine sample is going to be consisting of lighter chlorine and heavier, but chemically they're going to behave the same, right? It's just one weighs a little more than the other. If we look at fluorine 19 in nature, all the fluorine 19s look exactly the same. All right, now we're going to make this a little bit more complicated, because now we're going to add, look at bromine. There are two naturally occurring isotopes of bromine. Bromine 79, because this mass and percent natural abundance, and bromine 81. This mass, natural abundance. And what we're going to do is we're going to do this. We're going to make a molecule of bromine chloride. If we make a molecule of bromine chloride, how many different molecules can I make? In other words, are all molecules of bromine chloride in nature exactly the same, or are they a little different? In other words, a similar question would be like this. If you drink a glass of water, was every water molecule you just consumed exactly the same as every other water molecule? Or are there different water molecules that you're drinking? There are different. Did you know some water molecules are heavier than others? So when you drink this, you drank some heavy water molecules and you drank some light water molecules. And how many different water molecules are there? That's a question I asked on an exam last semester. I'll give you last semester's exam back as a practice. But I asked how many different, if you were to drink a glass of water molecules, tell me how many different water molecules you just consumed. Well, we'll do an easier one. That one maybe 10% of the. Got it. Or maybe it was more. More than 10%. Okay, how many different bromine chloride molecules exist in nature? How do I figure that out? Well, how many different types of bromine atoms are there in nature? 2. How many different types of chlorine atoms are there in nature? 2. So how many different types of bromine chloride molecules can you build? 4? Is it 4? Well, we have to be careful. We have to be careful because of this. I want to know not only how many different types or how many different ones, I also want to know in what percentages they occur. Okay, and so how many and what percentage? Okay, so the way we do this is like this. You know, the easiest is just to just do it. There's bromine. What is there? There's bromine 79. There's bromine 81. Bromine 79, bromine 81, chlorine 35, chlorine 37. What's the average weight of chlorine? The average weight of chlorine is 35.45, or about 35.5. 35.5 tells me it's got to be 75% chlorine 35, about 25% chlorine 37, just based on where the average is. Because if it were 100% chlorine 35, it would be 35, right? And so what I do is I look at the range. 100% chlorine 37, it would be 37. And so the average is not 36. If the average were 36, it would be 50-50, right? The average is 35.5, about 1/4 of the way. Not halfway between, but 1/4 of the way. And so it's got to be 75% chlorine 35 to bring it there, and only 25% chlorine 37. Do you see how I did that? Well, how many different ones can you build? Okay, so we have two bromines. So let's start off with bromine 79. To bromine 79, what can I attach? I can attach either chlorine 35 or a chlorine 37, right? And so let's go with chlorine 35. This is like Lego. And then here, bromine 79 with a chlorine 37. So there's 2 different ones. These weigh different amounts. And then I can do a bromine 81 with a chlorine 35, or I could do a bromine 81 with a chlorine 37, or I could do a chlorine 35 with a bromine 81, right? Yes? And a chlorine 35 with a bromine 79. And then a chlorine 37 with a bromine 81, and a chlorine 37 with a bromine 79. Is that right? Yes?
I didn't make the switch.
Yeah, I'm building redundant molecules here because all of these I already have this one 8135. There's an 8135. It just right 180. That's redundant. How about this one? Same. They're the same, except there's a funny thing, you know, about the statistics, about the percentages. So we'll talk about that. Actually, let's talk about that next time. Let's have a quick. We're going till 35, right? Let's have a quick pop quiz for today. Today's pop quiz is going to be this. Okay, I want you to determine the percent methanol in a mixture that has a 0.9, what was it? Oh, sorry, 0.07900 grams per milliliter density. Okay, remember the density of methanol was what was it? 0.07914 grams per milliliter. Is that right? The density of ethanol was 0.07893
93.
or 94. Was it 93 or 94?
94.
94 grams per milliliter. Okay, I want you to do this, figure out the percent methanol and comment on the precision. You can work in a group. This is open note, open book, whatever.
What is it? The density you gave us, 0.0790.
Yeah, this is the density of the mixture. Okay, so go ahead and calculate the percent methanol and then comment on the precision. Just a simple comment about the precision, okay?